Take it away. Great. All right, thanks, Ken. Thanks, everyone, for being here. I am indeed going to talk about some stuff in de Sitter space, and part of the theme of what I'm going to try and do in this talk is to leverage the things we've learned about black holes in the past few years and see to what extent they apply to accelerating cosmologies. So I'm not going to review the sort of technical details of the black hole thing, but I'll kind of set up the problem and try and argue why these two systems, black holes and accelerating cosmologies, are thought to be similar. So let's start off with the simplest thing possible, which is a classical black hole, as discovered by Schwarzschild over 100 years ago now. This is something he wrote in a letter to Einstein at the end of 1915, because he was fighting in World War I in the part of Germany. He was a little optimistic here because he died less than a year later. But anyway, he discovered this solution, the Schwarzschild black hole, named after him now. And it's pretty boring. I mean, much of the exciting stuff about black holes in our universe has everything to do with how a black hole interacts with its environment. Okay, the binaries, accretion disks, all this stuff. If you isolated the black hole and you just let it sit there, it wouldn't do anything. It's there at all you want. It just sits there. Doesn't really evolve in any interesting way. This is, of course, the event horizon of the black hole. A quantum black hole, as described by Hawking initially, is much more interesting from that point of view. It evolves even if you isolate it from stuff, from the environment. It evolves by emitting what we call Hawking quanta. So there's a particle that the black hole emits. It has an entangled buddy partner inside the black hole. I'm cheating in this picture and letting you see past the event horizon of the black hole, but there is basically a pair creation. These are like entangled pairs. You could think of them as some entangled sort of bell pair. And the black hole loses mass, and it continues to do this and evaporates down, until we believe completely evaporates away. Well, of course, there's a point past which this calculation starts to break down. So we believe it totally evaporates away, and you're left with a bunch of entangled particles. Okay, and the other cool thing about a quantum black hole is that it's kind of like a gas in a box. It has a temperature and it has an entropy. This is the formula for the entropy. Famously, it scales like the area of the event horizon of the black hole. And we get excited about this formula because it has all these fundamental constants that we think are uniting various branches of physics that are important to understand the full nature of a black hole. I'm going to set these constants to 1 for the rest of the talk. I just wanted to introduce them once. Okay, the analogy with the gas in a box is slightly compelling, but currently is only thermodynamic. But you can ask the question Boltzmann asked, which is there an atomic description that sort of describes this the way it does for a gas? You know, for a gas, we think of the entropy as, well, the way Boltzmann thought about it, you keep fixed some macroscopic parameters, and then you think of all the ways you could change the microscopic constituents such that you still have those macroscopic parameters. So you had some atomic description for a gas in a box. And you can ask, somewhat poetically if you wish, what are the atoms of a black hole? That's the question you can ask. And that brings us to this idea, which I'll call the black hole central dogma. It's an old idea, ascribable to some set of authors, including these ones, which is that from the outside, you can think of a black hole just as something like a gas in a box. In particular, you can think of it as some ordinary quantum system with this dimensionality of the Hilbert space. Okay, this is the formula that we saw before. It's playing a slightly different role here in setting the dimensionality of the Hilbert space. And it evolves unitarily, just like some ordinary quantum system. I mean, it interacts with the environment. It's not a closed system, but other than that, it's just evolving unitarily. I call this a dogma because we don't know this to be true. There are certain, we have evidence for this from various points of view. Like if you consider very supersymmetric black holes, you can argue that the dimensionality of the Hilbert space is given by this. Well, various computations that support this perspective.
There is exponent.
Sorry?
Exponent of this area for GN is entropy, and dimension
I'm
is
sorry.
I'm sorry.
Yes, it is. Yeah.
So, Edgar, if it's wrong, what are the alternatives?
The alternative is that the Hilbert space is more like what the semi-classical picture might suggest. Semi-classical picture, if you have an evaporating black hole, there's a sense in which the volume inside the black hole is getting very big, and you can imagine all these semi-classical excitations in the black hole. So the entropy can be much, much larger than the area of the event horizon of the black hole.
Okay, so it's really and it's not by central dogma, maybe not, it's just described by quantum systems. So
this is the pretty key. This is the pretty important part.
Yeah.
This part, yeah. Yeah, that part is less of a dogma.
Right.
This part is maybe the most dogmatic part. I mean, the other part we don't know for sure anyway for a black hole in our universe or something. We believe it to be true. But yeah, that's the key part. Okay, the thing that we've learned in the past few years, or have some computations to support, I won't really get into those computations, but we believe that, you know, classically, of course, if something falls into a black hole, the only way to access it is to jump in and go after the thing that fell in. But now we believe that you can actually access the interior of the black hole just by remaining outside. That if something falls into the black hole, that information of what fell in comes out through the Hawking radiation of the black hole. Okay? There's various computations that support that perspective. And the idea is you do some very complicated thing on Hawking radiation, and you can really access whatever it is that fell into the black hole. Okay, but now I want to talk a little bit about the analogy between black holes and accelerating cosmologies. Here I've drawn a black hole again. Here's us, the observer. The red dashed sphere is the black hole event horizon. These arrows just represent the fact that space is collapsing. And it's collapsing so quickly that a photon is not going to make it out of here and make it to your eye. Okay, it's not going to make it out of this event horizon. It's trapped in the interior. Cosmology, in particular accelerating cosmology, is similar. It's a little inverted. Instead of space collapsing, it's expanding, and it's accelerating as it expands, so that you have an event horizon which now surrounds you, the observer. So if there's a photon that's sufficiently far away, it's not going to make it to you, because the space in between you and the photon going to be expanding and accelerating as it expands too quickly. So they share event horizons. That's the first and key similarity between black holes and accelerating cosmologies. But those horizons also have an entropy given by the same formula, area divided by 4g Newton, as first shown by Gibbons and Hawking. And they radiate, similar to black hole event horizons. So you can ask, and these authors first entertained this idea, do they obey a central dogma? Can you think of the cosmic horizon as just some ordinary quantum system with some finite dimensional Hilbert space? Is that a reasonable way to think of the cosmic horizon? Okay, you can ask that question generally. In this talk, I'm going to focus on, at least at the level of symmetries, what's the simplest example of an accelerating cosmology, which is de Sitter space. Okay. Here I've written down the metric of de Sitter space in what are called the static patch coordinates. They're nice coordinates because they make clear why the system has an event horizon. At r equals L, this GTT component is going to 0. So you can think of that as an event horizon. It covers a piece of the full de Sitter manifold. And here are the formulas for the temperature and the entropy, similar to how a black hole has a temperature and an entropy. Okay. So so far I've been talking about the similarities between a black hole and an accelerating cosmology. Now I should paint a bit of a cautionary tale of why this analogy is not great for various reasons. So first of all, in the black hole central dogma, I said this thing about the dimensionality of the Hilbert space being set by the area of the event horizon over 4g Newton. And cosmic horizons have a similar formula for the thermodynamic entropy, which I just wrote, the area divided by 4g Newton. But there's basically little to no microscopic support for this entropy as setting the size of some Hilbert space. I said in the case of black holes, for very supersymmetric black holes, we have calculations in string theory which support it as setting the size of the Hilbert space. For cosmic horizons, we don't really have anything like that. There are scattered calculations and ideas here and there, but I think it's fair to say there's no agreed upon picture for this, and it may not be true. Another thing is, the way we think about black hole horizons is in the old kind of, either the original sort of 't Hooft or Susskind way of thinking about holography, or even older, the way maybe Wheeler thought about these things. The black hole horizon kind of encodes what's in the interior. That's how we like to think about it. And you can ask, which side does the cosmological horizon encode? It's natural to say it encodes the part you can't see, the exterior, but then you have to ask, well, what's encoding the interior, the part that you're in? Okay, that's a question we'll touch on as I go along in this talk. Another difference is that the cosmological horizon is both more universal and more observer dependent than the black hole horizon. What do I mean by that? By more universal, I mean that if you just take Einstein gravity with a positive cosmological constant and solve for the quote, vacuum solution, it's just de Sitter space. De Sitter space has the cosmic horizons in it. Whereas black holes, in particular in ADS, we think of them as excitations above the vacuum. So they're particular solutions of the theory, which are excited, which we think have horizons. So in that sense, it's more, the cosmic horizon is more universal. It kind of is coming along for the ride. It's more observer dependent because everyone who stays outside of a black hole is going to agree about the event horizon of the black hole. Someone who jumps in will have a different notion of an event horizon, but if you're outside, you're going to agree. Whereas in an accelerating universe, different people in different patches of the universe can have different observer horizons. So it's more observer dependent. Important technical thing, which is relevant for holography or other computations, like these ones I was referring to about accessing the interior of a black hole, is that in de Sitter space, for example, there's no asymptotic region at fixed time where you can ignore the effects of gravity. If we have anti-de Sitter space or flat space, you can take a fixed time slice and go sort of very, very far away and say that the effects of gravity are weak in a particular sense. But de Sitter has a closed spatial slice. There's no sense of getting very far from anything. So the back reaction on the system seems to always be important in de Sitter space. One other thing which I'll bold because I find it to be a very cute puzzle, and with Adam Levine, we wrote a paper trying to explore some aspects of it recently, which is that I said in the case of black holes, by staying outside, you can encode or decode, or however you want to phrase it, the stuff that fell into a black hole. If an elephant fell into the black hole, you can stay outside, do some sort of complicated manipulations, and access the information of that elephant. Now, if something like that were true in cosmology, which again is part of the type of question I'm interested in, it would be a little weird because two different observers with two different horizons, if they could encode the exterior of their horizons, the parts they can't see, those regions can overlap. So they can both encode the same sort of part of space-time. In a way that you can make precise, that's going to lead to paradoxes. For example, if there's an elephant in this shared region, both of you can sort of encode that elephant, meaning both of you can create that elephant in your observable lab and come together and voila, you've cloned this elephant. So it leads to violations of things like no cloning. But this comment is really maybe more for the experts. I think it's a cute puzzle which is going to sort of limit or control how these things we've learned about black holes can possibly extend to the cosmological setting.
Because they can't really meet, right? Because they live in different parts of the cosmological universe.
Well, they can be separate for a while, and then you can set up things where they meet later.
Unless, so that assuming that the Sitter place ends eventually, right? So that it's not eternally in place in the universe.
Yeah, that's right. Yeah, you can set up something like that where they meet later. Even if they don't meet later, if you want to say what you said, you need to rely on this thing that like it's a contradiction, but it's not an observable contradiction,
right?
Which is possible, but that to me that's still uncomfortable if that's the sort of resolution. Okay, and even if they don't meet, there are even sharper paradoxes you can draw. I mean, we can talk about those offline. But anyway, and there are lots more. Anytime I give this slide, people like to add their other reasons of why things in de Sitter are very complicated. So let's just, unless you're dying to express an opinion, I have shoved those objections into these ellipses, but there are lots of potential objections. But now I've aired my dirty laundry, I can kind of go ahead and talk a little bit about what we're going to try and do. First, I should sort of review the various approaches to holography for de Sitter spacetime, because the stuff I'm going to be talking about is somewhat holographic in spirit. So it'll help to kind of review these ideas. And there are sort of three sets of ideas that have been explored. So here I've drawn the de Sitter Penrose diagram. Okay, it's a square. And here the horizon's relevant for an observer that is living here, the origin of what's called the static patch, which is this diamond, or an observer here. This is their horizon.
Sorry, Edgar.
Yeah.
I get back to the previous slide.
Yeah.
No, I had a question about what did you mean there no asymptotic region at fixed time? Because if you're in de Sitter, that even there is no asymptotic region. Period.
Oh, I mean at future infinity, people often think of this as like an asymptotic region where the conformal boundary is, where you kind of think of gravity as being weak. Like if you exit from inflation or something, and then you're like
So
looking back.
but for that you need to exit from inflation again, right? Because if you're not exiting from inflation, that really it's not a good asymptotic region because it's.
Well, you can still think of gravity as being weak up there. Like if you look at things across many observable horizons, if you allow yourself to do that, like a meta-observable, then you can kind of think of gravity as being weak for that meta-observable. For any observer, yeah, it doesn't matter. I mean, they have a time translation symmetry effectively, so yeah, it doesn't even help to go to late times. Yeah, and that's actually related to this first thing, which I'll talk about in a second. Yeah, so this is the De Sitter-Penrose diagram. These are the horizons. These are what are sometimes called Bussell wedges. You can ignore them. They're just telling you where, like, which direction light sheets are focusing in, but you can ignore those. I'm not going to use them. And often we talk about a holographic dual being located somewhere, like an ADS CFT. We say that the dual theory is located at the ADS boundary. Okay, so the first question you ask, you write it down in Penrose Diagram, you ask, where should I think of the holographic dual as being located? This language is a little bit heuristic, but a useful guide. The very first thing people did, sort of almost immediately after the discovery of a positive CC, is to locate the dual at the natural conformal boundaries of the space-time, which are here and here, okay? These lines, these aren't really conformal boundaries here because each time slice of global De Sitter space is a sphere. So this is like the north pole of the sphere, that's like a south pole of the sphere, just fix your orientation. But the conformal boundaries are here and here. So you think of them like ADS boundaries and you say maybe the holographic dual is located on this pair, or if you want to ignore the past of De Sitter because it's not really relevant for our universe, you say maybe the dual is located up here. Okay, this was called DSCFT, and this the way I phrased it was really kind of put forward by these authors, and it was many years before there was a concrete model which was written down by these authors. It's a very messy model. But it was the sort of first concrete proposal, and okay, we generalized it some family models in this paper, but the model describes some kind of crazy theory of gravity in the bulk called Vasilev gravity, which has higher spin fields and is very complicated to play with. So it's hard to compute things in these models, and various computations were done, but it's hard to go too far with this. So I'm not really going to be talking too much about this approach, but it's probably the most commonly known one. Another approach is to locate the holographic dual near the static patch observer, by which I mean the person who lives over here or over here. Okay, there are various sorts of ways people have thought about doing that. Here are just two papers I put where people explore this idea, but the intuition is roughly that this region is kind of like an ADS boundary. For example, you could imagine having some De Sitter space-time which lives in an asymptotically ADS space-time, and then the boundary will live at those ADS boundaries. And that kind of transition region, you can imagine it happen over here. And so the dual theory lives somewhere then over here. That's somewhat of the intuition for that picture. And the other idea is to locate the holographic dual near the cosmic horizon. This horizon or that horizon, for example. And this is kind of in line with the original thinking of holography for black hole. The sort of degrees of freedom or the bits or the qubits live on the horizon, to say it somewhat heuristically. So you sort of say the same thing over here. These proposals, the second and third one, are observer dependent. This one explicitly, I have the word observer in there. This one almost explicitly. The horizons, as we discussed, are observer dependent. Okay, so these two are observer dependent statements. This one is not, but it's kind of refers to a meta observer. This slice, cuts across the horizons of different observers. This observer, that observer, some observer that maybe goes up here. So it's sort of a meta observable statement. In this talk, I'm going to be focusing on these two approaches. Any questions before we get into some of the computations?
So in the first approach, what is the CFT? How does the CFT encode information of the entropy?
Oh, we don't know. No one knows. That's something that people have explored. It's a difficult question to ask in the first approach. Maybe that's why you're asking it, because since it refers naturally to this meta observable that cuts across many horizons, it's a little hard to extract from it horizon physics. Mm-hmm. So that's why these two are a little bit better suited to trying to say something about the entropy. Although there's an interesting calculation in the one concrete duality that exists of at least getting the kind of scaling with n correct of the entropy. Ananos and Denef and some collaborators have done, but it's difficult to see it. Any other questions? Okay. I should give one quick review slide of the basic technology that I'm going to use. It comes from ADS CFT, and it's basically an idea of how to compute entanglement entropy in the dual field theory. Okay, the entanglement entropy of the dual field theory is computed by extremizing a particular quantity. So here's the entanglement entropy. And here I have a picture of ADS CFT. So here's the ADS boundary, and I'm computing the CFT lives on this boundary. And I'm asking about the CFT entropy of the reduced density matrix within, let's say, this dashed circle. Okay, so you can write down a density matrix here, which I'm going to call rho CFT. I want to compute the entropy of that density matrix. And the way I do it is I extremize this quantity, which we call the generalized entropy. The area is the area of this pink surface, and S matter is the bulk matter entropy within this pink surface. Okay. So in the bulk picture, you can define also a reduced density matrix here and compute its entropy. You add it to the area of this pink surface, and you extremize it with respect to the shape of this pink surface. Okay, it has to be anchored to the ADS boundary on this dashed circle. And when you find the extremum, that combination gives you the entropy. And if there's more than one extremum, you take the minimum one. Okay, there's a key physical thing that we seem to have learned from this picture, which is the notion of entanglement wedge reconstruction. And that says that in this duality between the CFT that lives in the boundary and the bulk, there's a sort of sense of a subregion duality. You don't need the whole CFT and the whole ADS space-time. You can talk about how subregions are dual to one another. In particular, the data within this pink surface in the bulk is reconstructible or dual to the CFT data here. You don't need to know about stuff over here to make statements about the bulk information within this pink surface. Okay, that's known as entanglement wedge reconstruction. And if that's true, which we have a lot of evidence for it being true, there has to be a basic consistency principle that's guaranteed basically by GR, which is entanglement wedge nesting. Which means that if I probe more of my CFT region, if I make this dashed circle bigger, then the pink region should get bigger. Okay? That's just like if you assume this, then that's just like a logical consistency principle. If I have access to more of the boundary description, I should access more of the bulk description. Okay? And that's something you can check in ADS, and it's true in every example we know of.
I have a question here. So
Yeah.
that you cannot construct the, your pink elephant paradox in this situation where you have overlapping regions that are.
No, you can't. Good. Yeah, here you have something, it's basically called complementary recovery, but in the end it boils down to if you took two disconnected, like this dash circle, and you put another dash circle somewhere else, they would never, those entanglement wedges, these pink spheres would never overlap. That's basically provable under some energy conditions and stuff in ADS. Yeah. Good question. Okay. All right, so I gave some of the conceptual background, introduced the technical tool that we're going to use. So now let's talk about the sort of first computation, which I'll lay out. So it hasn't escaped many people who've thought about de Sitter space that its causal structure, its Penrose diagram, looks just like the Penrose diagram for an eternal black hole in ADS. Okay, so here are the singularities of the eternal black hole. And the Penrose diagrams being the same means the causal structure is the same. The geometry is totally different. Okay, this one has singularities and it's otherwise just a very different geometry, but causally it's similar. And so we want to use that analogy. How do we want to use that analogy? Well, in these computations I was talking about where we learned that you can access what's behind the black hole horizon, it was helpful to append to this eternal black hole Penrose diagram some flat space regions. So recall that these lines here are now the ADS boundaries in the eternal black hole in ADS. So you can append to that boundary region some flat space region. Okay, the flat space Penrose diagram is a triangle. You can add this region on both sides. And I've grayed it out because basically we're going to ignore the effects of gravity here. Here you imagine you're sufficiently far from the black hole, gravity is weak, and we're going to basically imagine that it's actually totally shut off and we can ignore the effects of gravity. Okay. that was helpful in the black hole computations. What can we do here? As I said, these vertical lines are not conformal boundaries. Space is ending here. Well, you can do something that is going against one of the points of my cautionary tale. You can imagine carving out a little region near a static patch observer where you ignore the effects of gravity within those regions. Okay, this is not a good assumption because, as I said, you shouldn't be able to ignore the effects of gravity in de Sitter space. But it's meant to mock up something more realistic, which is if you have de Sitter space in an asymptotically ADS space-time, and then you could append these flat space regions to that asymptotically ADS space-time. So under more controlled or UV complete type examples, this is reasonable, but this here is just meant as a heuristic for those cases. Don't worry too much about it because the lesson we're going to learn is going to be more general than this particular example. Okay, I mean, feel free to ask me about it, but it's best not to stress about it at this point. Okay, we want to compute entropies, and it's very useful. It was useful in these black hole computations. And it's generally very useful to make sure you know what entropy you're computing. And for that, it's very helpful to think of what the holographic dual description is. Here we have control over that. We have this, this eternal black hole in ADS is understood to be dual to a pair of quantum systems in what's called the thermal field double state. It's just a particular entangled state. They're very entangled with one another. These semi-infinite lines I've drawn are basically the field theory that live in this flat space region and this flat space region. Okay, that's what these semi-infinite lines are. And this quantum system is interacting with this higher dimensional field theory by some couplets, which aren't going to be relevant. And this whole thing is in the thermal field double state with its buddy over here. Okay, that's the holographic dual description of this bulk spacetime. So what do we say over here? Well, here we're adopting this assumption of holography as being, the holographic dual being near the static patch observer. So we say the same sort of thing. You have a pair of quantum systems in some entangled state that's describing this red region where you can't ignore the effects of gravity, and it's coupled to some higher dimensional theory. Now it's not on a semi-infinite line because here you had this semi-infinite piece of flat space. Here you just have some finite interval. So you have some higher dimensional field there on some finite interval, and it's in an entangled state with its buddy over there. Okay, this is the assumption. Yeah.
If the higher dimensional theory is on the interval, you just specify the boundary condition at the other end. So what boundary condition do you put, or it doesn't matter?
Imagine space is just kind of capping off there in the same way that in de Sitter space. This looks a little funny because it looks one-dimensional. But you can imagine it's a higher dimensional theory, and space is really just kind of capping off at that point.
Okay, so it's not really a boundary.
Yeah, it's not really a boundary. Okay, so now let's say a few things that we've learned about the black hole case and see if they apply to the de Sitter case. In these examples, and even older examples actually, we've learned that you can interpret the black hole entropy as an entanglement entropy between the two systems. So the way that works is you compute the following entropy. You say, in the microscopic or in the holographic dual description, I want to compute the entropy of this system, one of the two systems which are in this entangled state. Okay. The way that works using this tool that I talked about before of extremizing this generalized entropy and finding a surface and blah, blah, blah. The way that works is that extremal surface that you find sits right at the black hole event horizon. Okay. It sits right at the black hole event horizon. So you pick up the area of the black hole event horizon plus the matter entropy along this surface. So you then interpret effectively the black hole area as an entanglement entropy between this system and this system. Or if you want, in the bulk between like this diamond and this diamond. Okay, that's a computation you can do. And in particular, if we remember the statement about entanglement wedge reconstruction, what it says is that this single system on its own encodes this region of the bulk. It can't really encode any of the interior or any of this region. That is really sort of the domain of this system. Okay. So what happens if you do the same computation in the cosmic case that I set up? Well, it looks like you get the same sort of answer. You find, if you do this extremizing I was talking about, that the extremal surface sits right at the cosmic bifurcate horizon, which seems good. It seems like you could interpret the cosmic horizon area as an entanglement entropy between these two sides. One, causal diamond of a static patch observer and the other causal diamond of the antipodal static patch observer. So it seems promising. Okay, this cosmic bifurcate horizon is, of course, an extremal surface in a similar way to the black hole bifurcate horizon. So that's exciting, but it's a false idol because there's a problem. And the problem has to do with this basic logical consistency principle I was talking about of entanglement wedge reconstruction. If I shrink the region that I'm probing, let's say in this way, now in the black hole case, then the region of the bulk I have access to should also shrink, right? And in the controlled ADS-CFT example, that's of course what happens. Since I brought in the right endpoint, I didn't include the full semi-infinite region. It's sitting somewhere here. The left endpoint now also comes in. So I access less of the bulk. That's good, that's what we expect. In the cosmic case, it goes the other way. If I shrink the region by bringing this point in, this point here goes to the left. So this example violates this entanglement wedge nesting. And there's a simple way to understand why that is. This cosmic bifurcate horizon, though it's an extremal surface, like this black hole bifurcate horizon, its nature is completely different. This surface, you could think of as being a maximum in time and a minimum in space. Okay, the way to understand that, for example, the maximum in time, space is collapsing and crunching down here and up here. So the areas are going to zero. And so they're increasing as you go up, and they're kind of maximized right in the middle. This picture is Z2 symmetric. It's maximized there, so it's a maximum in time. Why is it a minimum in space? Well, imagine the Einstein-Rosen wormhole that you think of. You know, it's a big circle, it shrinks to some minimum size right at the throat and grows again. So it's a minimum in space. This extremal surface is the opposite. Okay, the de Sitter diagram is something that's infinitely big in the past, shrinks to a minimal size at t equals 0, and becomes infinitely big again. It's a minimum in time, and it's a maximum in space, basically because this, you could think of this surface here as like a great circle on the sphere. You know, the horizon is surrounding us. So the fact that the nature of that surface is different means that this is always going to happen. That when you sort of fiddle around with these regions, this endpoint is going to react in the kind of opposite way to this endpoint. That's not obvious to see from what I've said here, but it's true. So it seems that using the de Sitter horizon and trying to interpret it, its area as some sort of entanglement entropy is not going to work. Which is not great because this is still, I mean, there are lots of other reasons to think that this is a reasonable, not a lot, but there's some other reasons to think that this is a reasonable interpretation. But at least from this perspective, you can't do it. So that's sort of the first lesson I wanted to convey. Any questions about that? Yeah,
So is there an argument for why the Takanagi formula, I mean, with the matter contribution added, would apply in this case?
Good. Yes.
I mean, this argument, this problem that you discussed is a consequence of that prescription.
Right? Good. Yeah. So, good. Let me say two things about it. Yeah, so the initial derivation, the Ryu-Takanagi prescription, and all the generalizations when you add matter and stuff, really, they don't use anti-de Sitter space so much as they use the assumption of having some holographic duality. If you assume some equivalence of partition functions, that's sort of enough. So here, that is of course an assumption I'm making, equivalence of partition functions. So one thing you can say is, well, that's just not how holography works in de Sitter spacetime, and that's why this didn't work. So that's one possible out. But if you assume the holographic duality looks like this, then the prescription should go through. The next thing I want to say is that I actually cheated here. It's true that this is an extremum, but the thing I said about it being a minimum in time and a maximum in space actually means that you should not use it in these entanglement entropy computations. There's a more precise thing you should say about why, when you derive this prescription, why you shouldn't use this kind of surface. But it seems to be true. I mean, it's an underappreciated thing in the literature of these sorts of computations because we don't really think about these surfaces in ADS-CFT that much, so no one's really spent a lot of time thinking about them. But this is actually not an appropriate surface to use in a computation of entanglement entropy. In a sense, what you really want to do is minimize on this time slice, not maximize. And if you do that, this endpoint's going to want to kind of shrink all the way over here. And that's, in a sense, the actual right answer to this problem. It's not a useful answer, but it's the right answer. Yeah.
But that will make the connection between entropy and the cosmological horizon and
Exactly. Yeah. Any other questions? Okay. But as you found emphasized, we want to maintain the connection between the cosmic horizon and entropy. So we're going to try and do things a different way. All right. And we're going to try to do things a different way, which is the sort of, in my list of the 3 forms of holography, think about the sort of dual being on now the cosmic horizon. This was like the 3rd option. Okay. And this one's going to be more promising, this approach. So I'm not only going to talk about failed approaches. This one is well, unclear if it's successful, but it hasn't failed yet. All right. So dual theory lives on the horizon. And the first question you need to ask is something I already brought up at the beginning of the talk, which is which side of the horizon does this dual theory encode? Okay, the reason this is a little funny is that in ADS-CFT, you have the ADS boundary, the CFT lives there, and there's only one side to the ADS boundary, and that's the side that the CFT encodes. Okay, you can call it the interior by convention. The CFT encodes that side. If you say that the dual theory is on the horizon, there are 2 sides of space-time to the horizon. So you need to ask, does it encode the outside, the inside, neither, both? It's a question you need to understand the answer to. But this, I think, is not actually a confusing thing. Even though I just said in ADS-CFT there's only one side to the ADS boundary, you could construct examples where there are 2 sides to the ADS boundary. And let's talk about that, how you do that, how you construct that example. So here's the picture I had before. You have the eternal black hole in ADS, and you have these flat space regions that you append to the Penrose diagram. And the holographic dual, or the microscopic description, is a pair of quantum systems, which you think of as being dual to this gravitating region in the bulk. And then these semi-infinite regions correspond to these semi-infinite regions here. And they're in some particular entangled state. Okay. You can modify this example. The simplest way to think about it is to modify the microscopic picture. Instead of having a semi-infinite CFT that's interacting with this holographic quantum system here, you make it some finite CFT, and you cut it off with some other holographic quantum system. Okay. And then you put this entire system in a thermal field double state with a copy of itself. That's something you can do, and we know what the bulk dual description is. Now, since you have 2 holographic quantum systems, red and blue, you're going to have 2 bulk eternal black holes, red and blue. The Penrose diagram now is identified between here and here, so it has like a cylinder topology. So this is the new Penrose diagram, and the kind of non-gravitating region are these finite regions over here. Those correspond to these finite regions here. Now, okay, it's not surprising what I'm going to do next. You can shrink these regions to 0 size, or a very small size if you want. What's going to happen is that this region is going to shrink to basically a single ADS boundary. Of course, there are some things you have to be careful about in actually trying to take this limit where this thing disappears. But I just want to illustrate that you can have situations where you have an ADS boundary and you have space-time to both sides of it. And there's no real puzzle here, okay? This system, or at least this pair of system, encodes the entire space-time, meaning it encodes both sides of the ADS boundary. Okay, this color changed because red and blue make purple. That's why it became purple. But you can think of this system as sort of being dual to both sides of the ADS boundary. Same for this system. Okay, so there's no real puzzle here. And if you want to compute entanglement entropies and find extremal surfaces using the Ryu-Takanaga prescription I was talking about before, you have to find extremal surfaces on both sides of the ADS boundary. In the picture I had at the beginning of the talk, which I'll just go to real quick, I just had it on one side of the ADS boundary because this is the canonical case. But now you're going to have to find another surface on the other side of the ADS boundary as well. That's what the rule is in this case. So in analogy to that, I want to think about de Sitter spacetime in the same way. You think of the holographic dual or the microscopic theory as living on this pair of horizons. Okay? Another way to visualize it is you take a global time slice, let's say this one. As I said, the global time slices are spheres. There's a sphere. Here's the left horizon. That corresponds to this region here. So this is like a DS3, a 3-dimensional de Sitter Penrose diagram. So time slice is a 2-sphere, and a horizon is therefore a 1-sphere, or a circle. Here's the right horizon, which corresponds to that circle living there. I'm going to call this region the exterior, that's this region here, and this is the left interior, that's the right interior. Okay, it's going to help. It's just a visual aid. It doesn't mean anything, so don't stress out about it. It's going to help to kind of break apart these regions into separate regions just to visualize what's going on. Okay, in the computations, it'll just make some things a little cleaner. Okay, but that's what a global time slice looks like. And the way I've set things up, in analogy to the ADS case, is that the rule for computing the entanglement entropy of this microscopic theory, which lives on this pair of horizons, is just going to be like this Ryu Takanagi type rule, where you find these extremal surfaces that live on both sides of the horizon. Okay, and the way I tried to motivate it, you extremize on both sides of the horizon, and in a paper that Lenny Susskind and I wrote together, we called that the Bilayer Proposal. Okay, so I wrote a paper where I computed things and argued for computing things this way. Lenny independently had a paper where his prescription is to not find extremal surfaces on both sides of the horizon, but only find extremal surfaces in the exterior region, okay, meaning this region here. And in the paper we wrote together, we called that one the monolayer proposal. These are just names. There's a reason they're named this way, but there's no need to worry about it. But a priori, these are two different prescriptions of how to compute entanglement entropies for the dual theory, which lives on this pair of horizons.
Sorry,
Yeah.
this one, but is it okay to put the theory on a null surface? Like the boundary, you know, it's boundary. This is 45 degrees, so
Yeah.
so it lives like where photons live. Can we define a CFT on a null surface?
Okay, so I have several things to say about it. It's not clear to me that there's a CFT that lives here. B, it's of course tricky to talk about any theory that lives on null slices. Of course, when people sometimes think about flat space holography, they like to think this way because you have Scri plus, which is a null surface. But it's tricky. I mean, one way people like to think about it is you regulate it slightly to have a time-like slice, and then you imagine taking a limit. A limit is not unique. There are different ways you can take that limit, but that's one way to start trying to get a handle on it. But I'm not actually going to say very much about the time evolution of the system. I mean, I'm not going to have a microscopic description at the end, so I don't have to face this problem yet. But it is true that it's a little subtle to talk about quantizing on null slices, although people have done it in their various techniques. Yeah, any other questions? Yeah, for the purpose of this talk, you could imagine regulating these a little bit so that they're like time-like slices, so you don't really have to worry about this.
But with either prescription, you have physically different results, right? The different answers.
Well, now we're going to compute some cases and see.
Okay.
Yeah. Okay, so let's compute the simplest case. Here we're going to take pure de Sitter space-time. I've chopped it up into the three regions again, and I'm going to compute the entropy of one of the two horizon theories. Let's say the theory that lives on the left horizon. Okay. Now the rule is I need to extremize to the left of the horizon and to the right of the horizon. I need to find some minimal surface. Since I picked the entire horizon, I don't even need to anchor it anymore to the horizon itself. It's allowed to be a free-floating surface. So the way to think about it dynamically is you start off with the circle that lives here, and then you let it minimize its area. Then it's just going to shrink and slip off the end of this sphere and give you 0 area. Okay, that's the right answer. The extremal surface that's homologous to this circle at the boundary, which lives on this side, is just the trivial surface, which has 0 area that lives at the tip. Okay, so you don't get area from that, any area from that extremization. When you extremize to the exterior, it's actually not going to want to go anywhere because the area is bigger out here. It's just going to want to sit right on the horizon. Okay, and that gives you a contribution equal to the area of the de Sitter horizon. If you add that to 0, which is what we got from the other side, you'll get the area of the de Sitter horizon, and you have to divide these answers by 4g Newton. So that's what you get for the entropy of one of the two systems. The entanglement wedge, which is the region between the extremal surfaces, you think of as this shaded blue region. You know, one extremal surface, like the trivial one you think of that lives there, and this one here. The entanglement wedge, or the region that's encoded, is the region within one horizon. Okay, that's good. That sort of fits with, I think, what our expectations are which is that the entropy of one of the horizons should be the area divided by 4g Newton. That's a Gibbons-Hawking result. And it's reasonable that the region it encodes is the interior. I mean, we don't really know, but it seems to work like black holes. It doesn't really encode the exterior region. It seems that you would need the other microscopic system to encode that region there. This horizon theory only knows about the interior region. And another nice thing is that this this extremal surface is now, I didn't introduce this language before, it's now a maximin surface. This was this long rant I went on about how the de Sitter extremal surface that we used in the earlier computation was a minimum in time and a maximum in space. And that was bad. That led to these violations of entanglement wedge nesting. And actually there's a way to phrase the computations now such that it's no longer a minimum in time and a maximum in space. It's now a maximum in time and a minimum in space. Okay, there's a way to reformulate this extremization prescription such that that's true. Why do we want to do that? Well, basically we want to do that so we don't run into these violations of entanglement wedge nesting. And you can check it in examples. There aren't any violations. I don't know that there's a general proof, but there's some arguments, and empirically it never happens. So that's good. But that's like the simplest calculation or consistency check. The entropy of one horizon is the Gibbons-Hawking formula. What about the entropy of both horizons? The union of the two. That is actually going to be 0. When you extremize to the left interior, you're going to get the same answer as before. You're going to get 0. Extremizing to the right interior is symmetric. You're going to get 0 again. And now when you extremize in between, the way to think about it dynamically is you have these two circles now, and you can think of them as having opposite orientation, so they can come together and annihilate and still give you the trivial area surface. And another way to say it is that you can have a region whose boundary is the union of the extremal surface and the two regions whose entropy you're computing, and there you go. That's a region that does the job. But altogether, you get 0 for the entropy, and the entanglement wedge, or the region that's encoded, is the entire space-time now. This is also an answer that we like. We don't believe that the global de Sitter space has an entropy associated to it. We think that that comes from tracing out some stuff, the stuff beyond the observable horizon, say, and that the global state is just some pure state. Okay, so the fact that we got the entropy of the full thing being 0 is consistent with that. And of course, the full microscopic description should describe the full space-time almost by assumption, and it does. So those are some consistency checks. And this was computing things in the kind of bilayer way that I was saying, where you extremize on both sides of the horizon. But if you compute in the monolayer way, you get the same numerical answers. Basically because the monolayer way of computing things just doesn't do the extremizations to the interior regions. But the interior regions never gave a contribution to the answer. I just got 0 every time I did that extremization. So numerically, you're going to get the same answer. Okay, so far, to answer Ken's question, we get the same answers from both prescriptions. Any questions about this computation? I'll do a slightly less trivial one in a second, but if this one's unclear.
Again, can you monolayer theory? What are you calculating? What is only one side?
Yeah, you only find extremal surfaces in this region of the space-time. The name is a funny name. It just has this relation to a sort of something called the bit thread reformulation of these entanglement entropy computations. But just mono and bi just refer to like how many sides of the horizon you're doing an extremization on. And in monolayer, you only do it to one side, this side here. Any other questions? Okay, I'm going to skip that. You can repeat this exercise for a black hole in de Sitter space-time. Okay, the topology is slightly different, but you can compute and then you get, again, the answers that we expect, the sum of the black hole and horizon entropies and reasonable entanglement wedges. Monolayer and bilayer theory agree in this case. I'm not really going to go through that one in the interest of time, because I want to jump to an example which seems to differentiate the two proposals. And it differentiates them in, I think, an interesting way. And it corresponds to, instead of taking an entire horizon or an entire pair of horizons, taking a subregion of the horizon. In ADS-CFT, there's a totally reasonable thing to do. You compute the entanglement entropy of some geometric region of the CFT. In this case, it's not clear that it's a reasonable thing to do. It's a little bit like trying to chop up the internal space in ADS-CFTs. In ADS-CFT, we have like a ADS5 cross S5 or other internal manifolds that are in the game. You can ask about trying to like divide those things into pieces and computing entropies between them and trying to interpret them. People have tried. It's confusing. We don't know what the answer is. The de Sitter case, for reasons that I won't get into unless somebody wants to ask me offline, it's a little bit more like trying to do that, trying to chop up this internal space. And it's not clear that that's a reasonable thing to do. So that's just my warning for this computation. But it's interesting, so we're going to compute it anyway. And let's see what happens. So the red region is the region whose entropy I want to compute, okay? So I'm going to compute it in the bilayer theory first, or the bilayer way. And you want to extremize to the inside and to the outside. And what actually happens, even though this is a terrible picture, which doesn't show clearly why it happens, is that the extremal surface you're going to get is just the region whose entropy you're trying to compute. Okay, that's where the area is actually minimized. It's not actually going to move at all. So you're going to get two factors of the region of the horizon that you chose. Okay, one factor from the interior extremization and one factor from the exterior extremization, which means that the entropy is going to grow too fast. What do I mean by too fast? What I mean is at the halfway point, the entropy is going to equal the area divided by 4g Newton, because you're going to get two factors of half the horizon area. That's not good, because the central dogma of de Sitter space would be something like the Hilbert space is set by the area divided by 4g Newton. This is exactly the problem we run into in the black hole information paradox. You collect the Hawking radiation, you measure its entropy, and it seems to be too large. Its entropy seems to be larger than the Hilbert space of the black hole. And that's impossible, because you can't be more entangled than there is stuff to be entangled with. Okay, that is just a violation. This smells like a similar sort of problem. Okay, you're going to exceed this thing. Of course, here it's much more of an assumption that the Hilbert space is set by this function. But in any event, there seems to be this problem if you go by that assumption. But also similar to black holes, a transition happens that saves there from being any problem. Because once you hit the halfway point, actually it's beneficial to pick a different surface for the interior extremization. Instead of picking this surface here, it's allowed to flip around to the other side and pick up the complement region on the horizon itself, right at the halfway point. And when it does that, when you add these two areas, you just get the area of the horizon divided by 4g Newton. So the entropy saturates exactly where there was going to be a problem. This also is just like what happens with black holes. You collect the Hawking radiation, the entropy is getting large, it's approaching the black hole area divided by 4g Newton. And right when it's about to violate that bound, there's a phase transition in extremal surfaces, and the entropy saturates at the area, in that case of the black hole event horizon, divided by 4g Newton, and stays there. Also similar to that case, the entanglement wedge goes from being none of the interior to all of the interior. Okay? The physics of it, if there's actually physics described to this situation, is going to be totally different. Doesn't seem like the physics should be at all similar. We're not computing the entropy of Hawking radiation here. But everything else smells very similar, which I find kind of intriguing and would be great to understand better. So this transition ends up allowing things to be consistent with the idea that the Hilbert space is set by this, the size of the Hilbert space.
So you are using the two layer.
Yes, I'm about to get to the one layer. That's right. Good. So let's get to the one layer in a second. You might worry that this curve is kind of a crazy curve. We think of de Sitter space as a thermal system. I said it has a temperature, 1 over 2 pi L, where L is a de Sitter length. And at thermal systems, we think of as having extensive entropy curves as a function of the system size. This is, well, what it isn't is an extensive entropy curve. Okay, it saturates at some order 1 fraction of system size and stays there. So this is not how an extensive or thermodynamic system behaves. So you might worry that this is inconsistent with general expectations of what de Sitter space is. And if you're worried about that, you would be encouraged by the monolayer answer, which says that you need to forget about this surface I was talking about on the left side. You only compute the area of this surface, and that one only grows, it grows extensively, it grows exactly as a fraction of the system that you're considering. In particular, it's this green curve. This is an extensive entropy curve. So you might like this answer more. But in the last 5 minutes, let's say, I want to argue why that's a little too quick, and this is actually not an answer that you would want. Okay. And to talk about that, we should somewhat remind ourselves of what we mean when we say something is a thermal system. In particular, we've gotten used to in ADS CFT talking about the large N limit as something like a thermodynamic or a large volume limit. Okay, it's not. It behaves similarly to it, but it's not really. For example, we talk about black holes as being thermal states and things like that. And okay, why do we often say that it's like a black hole is a thermal state or use such language? Well, there are different ways to think about it. One way to see why we use that language is imagine taking, let's say, n equals 4 super Yang mills or some higher dimensional CFT and compactifying it on a torus, something with some length scales. Okay, then you can compute the entropy of this system, and in an ordinary system, the entropy would have the sort of leading extensive piece, which looks like this. That's the thermodynamic answer, the large volume answer. But it can have a host of subleading, subextensive corrections. Okay? And in general, theories do have these subextensive corrections. But for interesting reasons that I think are related to certain higher form symmetries that exist in holographic theories, they don't have these subextensive corrections, even though they could. So this is the answer. Even when you're not at infinite temperature, as long as you're above the Hawking-Page phase transition temperature, you're above the confining deconfinement phase transition temperature, this is the full answer, even though the theory has finite length scales that could combine with the finite temperature and form dimensionless numbers. Okay, so there could have been power law corrections, but they're not there. So large N theories act like they're in the thermodynamic limit, even when they're really not. Okay, thermodynamic limit would mean infinite temperature. But we can be at an order 1 temperature and still have answers that look like they're thermal answers. Okay, they're good at mimicking thermodynamic limits, but they're not amazing. You could compute pretty simple things, which will show you that it's not an ordinary thermal system. So here I've put a black hole in ADS. Here's the ADS boundary. And I'm computing the entropy of a subregion of the CFT, let's say subregion R. Initially, for small region size, I just pick up the UV answer. It can't even tell that the black hole's here because the surface is close to the boundary. As I make the region bigger, it starts feeling this infrared scale, this temperature, black hole. And as I make it bigger, it starts to feel it more. And then at an order 1 fraction of the system size, there's a phase transition. It disconnects into a union of this surface and a surface which hugs the black hole horizon. As you make the region bigger, this surface remains, and this one just kind of keeps shrinking. Okay? So this is also not an extensive entropy curve, and it's because a black hole, even though we call it a thermal system because it looks like one, is not actually a thermal system in the traditional sense of the word, in the undergraduate, large volume thermodynamic limit sense of the word. The way to see how you get thermodynamic answers is to take the infinite temperature limit. If you did that, this black hole would get very big, it would get very close to the ADS boundary, and this transition would get pushed to arbitrarily, large system sizes. So then you would immediately get an extensive curve right away. If the black hole's all the way out here, right away, this surface would be hugging the black hole horizon and giving you that extensive answer. So large N limits are not the same as thermodynamic limits. And the point of this example is to say that de Sitter space is a lot like this case. We say it's a thermal system, but it's like a large N thermal system. Okay? And just like we saw here, you can have a transition that happens at an order 1 fraction of the system size. Here it's at exactly half the system size. In this case, it's like greater than half the system size, but okay, those are quantitative differences, not qualitative differences. So that was just a plausibility argument for why this curve is not crazy. And now I'll end with microscopic theory, which is probably not relevant for de Sitter space, but which gives you this entropy curve from the bilayer theory. Let me just say real quick, one nice thing about this curve, like a practical or sociological nice thing about this curve, is it's somewhat constraining. You can start looking for a theory that has this entropy curve. That's like a way to try and search for a theory that might be relevant for de Sitter space. This one, even though it may be correct, is very easy to reproduce. Take any system you like, put it at infinite temperature, this is the entropy curve you're going to get. So it's not a very constraining curve. It's just has a single number associated to it, which is the slope of this line. This is a bit crazy. This is a difficult curve to try and reproduce from an actual, like, I don't know, large N interacting system. But let's try and reproduce it from not a large N interacting system. The dumbest system we can reproduce it from, the Heisenberg antiferromagnet. So you have two qubits, which I'm calling sigma and tau. J is some positive number, so the interaction is antiferromagnetic. This is an exactly solvable system. You can put this system in a thermal state. So the density matrix is e to the minus beta h, where h is this Hamiltonian and beta is some number you can tune. And you can ask about the entropy of 0 qubits, which is always going to be 0, of course, 1 qubit or 2 qubits. Okay. At 0 temperature, you're in a spin singlet state. You're basically in a Bell pair. It's a pure state, so the entropy of 2 qubits is 0, and 1 qubit is maximally mixed. You get log 2. Okay. At infinite temperature, you recover this extensive entropy curve that I was talking about. It's maximally mixed. Okay. You can ask, is there an intermediate temperature where I have this kind of turnover and I get the curve that I want? You might worry that the entropy of 1 qubit will move off this log 2 point, but actually this model is simple enough. There's an SU2 symmetry that enforces the entropy of 1 qubit being maximally mixed. So at any temperature, the entropy of 1 qubit is actually always log 2. Then, of course, there's going to be some intermediate temperature where the entropy of 2 qubits is also log 2. Okay, it turns out it's this number, some order 1 number, times j. Okay, it's of course easy to reproduce this curve when there's no structure in between these points. But I think the way that this model reproduces this kind of crazy curve might be similar to the way a theory dual to de Sitter space might. We think that those theories are sort of maximally non-local, perhaps some order 1 or large surface to volume ratio, or sorry, have an order 1 surface to volume ratio, similar to how this system is always going to have an order 1 surface to volume ratio. But anyway, it's just a simple model to show that at intermediate temperatures, you can have a curve like this. Okay, let me just end with just a summary. So the first lesson I tried to communicate is that the cosmic horizon is actually very different than the black hole horizon in a particular geometric sense. And this was the nature of where it was a maximum or a minimum in time or in space. And that difference means that it's not naively going to work as a classical or quantum extremal surface, as a surface that computes entanglement entropy for you. You can't naively use it as such a surface. But if you change the rules and think about the dual theories being on the horizon and you sort of anchor surfaces to the horizon surface, then it seems you can actually use the cosmic horizon area as an entanglement entropy and not run into these inconsistencies that I talked about in the first part of the talk. All right, de Sitter space in cosmology is kind of the Wild West as far as holography is concerned. The rules are very unclear. So it'd be nicer to have a more controlled setting where we can check these ideas. So it might be nice to kind of go back to thinking about black holes in the very, very old holographic or pre-holographic way, where you think of the degrees of freedom as being on the horizon itself. You can ask in ADS CFT, can we anchor extremal surfaces to the black hole horizon, not have to go all the way to the ADS boundary, but do something a little bit more local? Is that something we can kind of make sense of? Another comment which I didn't really talk about in the talk is everything I was saying about de Sitter space was very special to the fact that I was considering global de Sitter space, this Penrose diagram that's infinitely big, comes to some minimal size and bounces basically. Okay, a more general cosmology like the one that describes our universe, we don't have any evidence that it bounced, and the structure of how holography or things should look in that case is going to be very different. So it'd be nice to understand how encoding and holography should work in a more realistic space-time like that. I can say offline why I believe these two cases are very different. And the thing I care about the most is basically what I was talking about on the slide before this, is to try and come up with a microscopic model which matches these computations. In particular, this entropy curve that kind of flattens out. You can ask if there are quantum mechanical systems, SYK-like systems, which have that kind of entropy curve, because it's somewhat of a smoking gun almost. If you could find a large N interacting system that has that entropy curve, and you also believe for some other reasons is relevant for de Sitter space, that's pretty constraining. And the thing that's lacking in this subject is microscopic models. So that is something that I'm thinking about a lot right now, but I'll stop there. Thanks for your time.
related to this point about that it's important for you to consider eternal de Sitter.
Yeah.
One worry about it because eternal de Sitter tend to be kind of unstable because of this period of blue shift, right? So we think that's the reason we think in inflationary cosmology it's never like it always starts with a big bang, right? Only half of this square, right? So we are saying things change dramatically. Right?
Yeah.
You do that. So,
Yeah. No, I think it is important to consider. I mean, whether de Sitter is eternal to the past or whatever, has this Penrose diagram, let's say, I think in our universe, it doesn't seem like that's the case at all. But if you're just thinking abstractly in terms of whatever the academic problem, I think it's a theory-dependent question. I think it's possible that like something like a Vasiliev theory in de Sitter space or some, I don't know, some theory like that can have as a stable solution global de Sitter eternally. So I think it's a theory-dependent question that one would have to analyze. That's not so relevant because the reason we care about this problem is that it's relevant for our universe, and our universe doesn't look like it's bouncing. So then, yes, I totally agree that it is an important concern, and you need to understand how it works there. The reason why it was important in what I did, even though it wasn't explicit, is the fact that it bounces basically means that you can't. So I said that these two horizon theories, which have Hilbert spaces set by the area, encode everything in de Sitter space. You might think that's crazy because there's a ton of stuff you can put in your Scribe Plus. It's a huge inflating spacetime. How in the world is it going to encode that infinity of things you can put there? But because you've conditioned on the bounce, that means that you can't actually put too much stuff in your Scribe Plus. If you did, and you rewind time, it's going to crunch. So that bounce is kind of enforcing the fact that the Hilbert space is more limited than you might naively think. You can't put too much stuff there. If you start off with a bang, like we think in our universe, you can put as much stuff as you want in the bang, and you don't have control over the computation there. So then you can seemingly have an infinity of stuff in your Scribe Plus, and then it doesn't seem to me like there's some one or two finite Hilbert spaces which can encode all that. That's the dramatic way I think it'll be different. I think it's still possible that a theory can live on the horizon and encode the interior, but it's not clear that it should encode the exterior region by itself, or even with another horizon theory or something like that. But that case is even under less control. I mean, people like Banks and Fischler have thought about how to understand those cases, but like even though global de Sitter is a bit of a fiction, it might be a little bit like the thermal field double in ADS. Like it's a good toy ideal example to try and get your bearings on what the microscopic theory should look like, and then you might hope to use that to understand better.
Any other questions right here?
Just a quick question about the third point. So have you or any other people tried to do some computation associated with the lunar surface anchored at the black hole horizon in ADS and try to match with expectations?
Sort of. So the thing that I've thought about a little bit, although it's not clear how to. I initially thought ADS CFT would tell you something about it, but yeah, it's not clear to me that it does. You can consider the thermal field double black hole in ADS. That's often the simplest case to consider. And you can set up a similar sort of thing. Let's say you think of the horizon theories as living here, and you can ask, for example, about computing the entropy of the left horizon theory union the right horizon theory. And something interesting happens in the Bilayer proposal. You might say that the black hole theory should not encode the exterior region of the black hole, so you shouldn't extremize to the exterior. But you don't actually need to input that. That's an output. If you extremize to the exterior, it's not going to go anywhere. The area is bigger out here, so the surface is going to want to stay put right there. Same for this guy. So you'll get two factors of the area of the black hole horizon. And then when you extremize to the interior, it's actually going to come together and annihilate in the same way. There's going to be trivial surface, and the Intangible Wedge will be the region in the interior. That's good. That's okay. Seems like the right answer. And actually, the interesting thing is, in this case, the monolayer theory will give you a different answer. The monolayer theory will give you 0 for the entropy. And I find it very annoying that.
And the entanglement region in that case is again the whole slides?
In the monolinear theory, it's not clear you can associate notions of entanglement wedges because you don't have like closed regions you can
Right.
talk about because it's just like anchored to something that's floating in the middle of the space-time. But probably the reconstructed version should be that. So let me take two. Initially, I was very excited about this because this was a case that sharply differentiated the two.
Yes, yes.
But it turns out these are the only two answers that are possibly sensible. Like if you just ask this question, what's the entropy of this region? The only two acceptable answers are this or that. We don't know what the answer is, but these are the only two acceptable ones. This one is acceptable because there's this issue of the generalized entropy being a finite quantity because the gravitational piece and the matter entropy piece renormalize one another, whatever. For it to renormalize appropriately, this coefficient here is important. It has to be basically the area of the endpoints. So this is the correct coefficient such that the generalized entropy is a finite quantity. That's why this answer is sensible. Also, okay, there are two black holes. It's another reason why it's sensible. But this answer is also sensible because you might think that all the degrees of freedom in the full microscopic description are at the boundary. That's what ADS-CIP or holography says. So you can't even assign a notion of an entropy between some floating interior region and the rest because there's nothing there. That's like an emergent fiction. It's in your head. So this is the only other acceptable answer. So it's hard to disentangle these. But to get to more of what you're asking, can you check this with ADS-CFT? Yes. The tool I was hoping to use, although it doesn't quite seem to do it here, is there's a tool initially developed by Engelhardt and Wall and other people have studied, is to associate entropies to surfaces that are not Ryutakanagi or extremal surfaces.
Right.
So this is not an extremal surface.
Yes.
But you can imagine anchoring to the boundary by taking the complement. This whole thing's a pure state. So the entropy on the complement is equal. And you can ask, let me ask about the entropy of the union of these diamonds.
Right.
Unfortunately, that technology I was talking about can only associate a coarse-grained entropy, not a fine-grained entropy, to the area of these surfaces. So it doesn't quite nail the fine-grained entropy as far as I know. Now, maybe there's something clever you can do, but it doesn't quite seem to do the job. But this is how you might, I'm imagining getting close. You have something that's anchored to the boundary, and okay, clever, maybe you do something.
Okay, any other questions from Zoom, perhaps? All right. Now let's thank Edgar again for a great talk.